Okay. So we have a good break. Ready to be back. Anybody have any good travel stories?
You do.
Well, yeah, man. I went to a river cruise in France. I traveled somewhere else too. I don't remember. Played a lot of golf. Nobody went anywhere interesting. Just home.
Went to Ecuador.
Ecuador. Mm-hmm. What was an Ecuador mission trip thing?
Yeah.
How long were you there?
10 days in the Andes Mountains.
Hey, that sounds roughing it.
Well, part of the time, yes, and part of the time, no.
So a good experience.
Yeah. Except that the airline lost her bags. Eventually, we got the bags. So that was good.
Like the day you were leaving.
No, a couple days after they lost them.
There was one couple that was on the cruise in France that they lost their luggage and they got their luggage back just in time to get on the flight home.
We were pretty much at the point where we weren't expecting to see it again.
I see.
We finally figured out where it was.
Gotcha. I'm going to India next month to recruit grad students. So I'll be teaching 4 of our classes remotely. So we'll have class at normal time, but I'll be in India being projected up on something. And it's like 11 o'clock at night in India or something. It'd be kind of cool. Plus I'm going to teach the entire class in probably Urdu, I'm guessing. I'll pick up some language there, I'm sure. All right. So standard syllabus thingy majiggy. Is required text for the class, Zybooks. Go to zybooks.com, put in this link, buy the book. Book is definitely going to be required. We're going to be doing, we're going to be learning about computer organization and architecture in here, but we'll also be doing assembly language programming using ARM processors. And the book has a built-in ARM processor interpreter thingy-majig. And then we will also be writing our own ARM processor interpreter. Because why use one that's already built when you just write your own? Makes sense, right? Plus that helps us understand how instructions work and that kind of jazz. All right. So the usual 60% of your grade is homework assignments. Quizzes, pop quizzes can pop up. Haha. Those fall into homework grades. So, sometimes depending on the semester and what mood I'm in on a given day, we might only have 2 quizzes during the whole semester. In other semesters, we have 10. But if you miss 1 or 2 quizzes, it just falls into the big category with homework, so it shouldn't completely kill you. All right. Midterm and final, 20%. The usual policy, if you do better on the final than you did in the midterm, I'll replace your midterm exam grade with what you get on the final. Questions about any of that? The usual stuff. 90, 80, 70 grading scale, top and bottom 2% for the minuses and the pluses, blah, blah, blah. All right. Questions, comments, concerns, or bribes about the syllabus? Perfect. All right. As usual, we are a Christian university, so we incorporate a Christian worldview into the classroom. So every week you will have a Bible homework assignment where you'll have to read usually 1 chapter from the Bible and then write a 1 or 2 paragraph response to it and how it relates to your major. Sometimes the relation to your major might be very, very loose. That's okay. This is my way of forcing you to read the Bible. It's also basically free points, so there's no excuse for not doing these assignments. I try to get them up as early in the week as possible. They're always due at midnight or 11:59 p.m. on Sunday. If you're in more than one of my classes, the assignment is the same each week, so you can double dip, write it once, submit for both classes. That way I don't have to pick 2 different chapters. But if you'd like to pick a second chapter and write a different response, there could be extra credit in there for you, possibly. At least I still give you credit. All right. Questions about that? First homework's already up. It's due midnight Sunday. We're good there? All right.
Going up every Tuesday.
Ish.
Okay.
It would be in your best interest. I'll probably try to put it up on Mondays.
Right.
It would be in your best interest if you don't see it by the end of the day on Tuesday for you to message me on Slack and say, are you going to put it up? Because it only takes me a few minutes to put it up. But if I forget, then you might be in a situation where it's a weekend thing. But it shouldn't take you all that long, right?
Right.
Should be a 5 minutes of reading and then another 5 minutes of 10 minutes response, and life goes on. All right, so no excuses for missing those. Put a little reminder in your phone for each week, maybe on Sunday afternoon, to remind you that if you haven't done your Bible homework, remind you to do your Bible homework, because it seems like every semester you get this group of people that do 0 of them for long stretches of time, where this is like free points. Just do it. All right. All right. Questions about any of that? Okie dokie. So let's, I will put up the link for the videos after I have them up on YouTube, but I record all my lectures. They'll be up. Course slides is already linked. So this is CSC325, Computer Organization and Architecture, or something along those lines. What does that mean? What does computer organization and architecture mean? Just a fancy name for a class that makes it sound kind of difficult? That's what it meant to me. What's computer organization? When we talk about organization, our computers are made up of a whole bunch of parts, right? Okay, and these parts have to work together in some sort of interesting way to make our computers work. What are the parts that go into our computer? You in 175, you built some computer stuff, right? What are some of the parts you've heard of in your computer? What do they do?
Cooling unit.
Cooling unit.
Prevents it from overheating.
Okay, so like a heat sink thing, prevents it from overheating. We'll actually be talking about heat here in a little bit. What else?
CPU.
CPU. What's a CPU?
Central processing unit.
Well, that's what it stands for. What is it?
It basically does logic and all the magic that makes the computer work.
Okay, so it's a pretty integral part. Even if you have all the other good stuff, you're not going to do all that well without that guy in the center, right? So he kind of like a quarterback. He's passing stuff off to all these different places of the computer. And she mentioned lots of logic stuff. I've advertised the CPU as kind of being this collection of magic tricks that knows how to do these little tiny granular steps. And if you remember from like your 200 or 250 class, it's you think about, I just did this today, so it's fresh in my mind. None of you are impressed if I can move my hand like that. Right? Or if I can go like that. It's not an impressive thing, but if you do a bunch of those things together, you can reach out and you can grab something and do something. So I just solved a problem. So if you think of a human being kind of like a CPU, we have all these little widgets that we can do, these little tiny movements that we can do. If we put them together in an interesting way, we can solve a legitimate problem. And that's how CPUs work. So they got this giant list of instructions that we can call upon in a certain order, and a real task a solution to a problem might happen. And we're going to be learning about ARM processors in here. I'll talk about that here in a few minutes. Let me just throw that on I'll put it on this slide. I always put another one in. We'll talk about ARM here in a second. Okay, so we have CPU. Let me get back here. Computer parts. So CPU is pretty important one. Okay, and he said cooling units. So that's kind of the CPU's air conditioning, right? Go ahead.
Hard drive.
The hard drive? Okay, hard drive, solid state drive. What's that guy for?
It stores all your data as well as the operating system.
Store stuff. Store stuff. Compute stuff. All right, store stuff, compute stuff. All right. What else?
Power supply.
Power supply. Power stuff?
Power supply. It's the powerhouse of the computer.
Okay, so power stuff. Okay, all of our stuff works on electricity. Okay, so this guy makes everything light up. Okay, what else? Actually, we'll add it here in a few minutes. What other parts do we know about our computer?
Keyboard.
Let's go more internal in the computer. RAM. What is RAM? What does that do?
Read access memory.
Volatile memory.
Volatile memory. Oy. Okay, well, what does that mean?
Kind of hold like what the operating system is doing, so it'll like your different.
What does it mean for something to be volatile? I like that word.
Violent.
Usually it doesn't come up until week 2 or something. Temporary. So RAM, when we turn our computer off, anything that was in RAM is lost, right? So our hard drive is non-volatile, long-term, remember stuff so we might say store stuff slowly, but permanently. Ha! All right. RAM, store stuff fastly-ish, but temp. I encourage you to have all my slides double-checked by your English profs. Fastly-ish. Yeah, that's a good one. All right, so RAM, faster storage. A hard drive, slower storage. What about size? Which is usually bigger, hard drive or RAM? Yeah, you go out and buy the 2 terabyte hard drive at Best Buy on sale for $80. How much is 2 terabytes of RAM? You better have an expensive motherboard to house 2 terabytes of RAM. They do exist, by the way.
256 gigabytes is $4,000.
Of
RAM.
256 gigs is $4,000.
Yeah.
What kind of
It depends on the RAM. I think you can get it cheaper than that.
That's what I found.
Maybe ECC memory.
RAM for
Yeah.
464 gigabytes.
Yeah, but I bet you that's ECC memory, server RAM. But still, even non-server is going to be expensive. But RAM is relatively inexpensive in terms of the amount of storage that we typically purchase. 16 gigs of RAM, or if you want to be the cool kid, 32 gigs of RAM, something like that. Not that huge of an expenditure. Hard drives are much, much larger, but they're also slower in terms of storage. And we're going to see that pattern as we talk about that stuff in here over the first, probably this week actually, or at least into next week, where we talk about memory. Closer you get to the CPU, faster and more expensive memory tends to be, and also smaller it tends to be. Okay, and this is a very important kind of thing. We've only mentioned 2 different kinds of storage, 2 different kinds of memory here. We've mentioned the slowest and the second slowest. There's a whole bunch of more little layers that lead us to the CPU that gets faster and faster and faster and more and more and more and more expensive. All right. Anything else? Motherboard. What's that guy?
It directs power and information between different parts.
Hooks all the stuff together. Okay? Hooks all the stuff together. Now, we can think of a motherboard as kind of like a city.
As a what?
As a city.
Oh.
Cities have roads and interstates and things that connect them. Okay? What are roads called in computer terms? Bus. We got this thing called a bus. Okay, that's a road of connectivity between 2 points, and sometimes the buses split off because you have exits, right? You can go off 2 different places. All right, so if we think of our motherboard as kind of like the city where all these other parts live, we have various roads that go between the different components of our computer for accomplishing tasks, or for at least getting data from one place to another. Okay. Now, when you think about roads, like if we're going from here to Milwaukee, what roads do we take? What's the main road we take? 43. Now, why do you take 43 instead of Port? Faster. So we go, there's a higher speed limit, except for like the last couple of days. Wasn't 43, at least up this way, like flooded? Closed it down. There was water all over the road. But in any case, we have certain roads that go faster than other roads, or you're supposed to go faster. I've seen some people go pretty quick on Port. These buses, we have connectivity between different components of our computer. They have speeds associated with them, and sometimes we have governing protocols associated with them that say, well, things can only go at this speed on these guys because maybe we're not monitoring for errors, something like that. You know, if you're going down 43, there's probably some sort of, average speed you could go where, if you take out all other drivers and things like that, it's pretty unlikely you would like swerve off the road or something like that. Like if all of us went, you had the whole road to yourself and the conditions were good. If we went 50, it's a pretty safe, maybe kind of a boring speed, but not a whole lot's you have plenty of time to react to like, little wind gusts or something like that.'re fine, right? But if you're going 150, things become a little bit more sketch, right? Okay, so you might want some oversight, but depending on which bus we're dealing with on our computer, there may or may not be oversight on that bus, and we need to guarantee data gets from one point to another without errors. We need to maybe control that speed. Anything else with our computers?
I might have a graphics card.
GPU. Graphics card. GPU. Sort of kind of like the CPU. What's this guy? Compute stuff. This guy's compute stuff general purpose. This guy's compute stuff mathy. Go ahead. I missed who? Purpose general it's enough of it's there. Purpose. No, I didn't miss it. It did this. Ha! I told you, I had my disclaimer. I said, have your English teacher check all my stuff. As long as it's close enough, we're fine. You would see some of the handwriting after grading your tests. I'm winning this one. Those are the really funny ones when a teacher has to look at an answer test and you can't read anything the person wrote. And you have to do I pretend like I could read it and give them point? I mean, I think this started with a letter of the alphabet. Yeah, sometimes it's pretty bad. All right, graphics card. Compute stuff, mathy stuff. So why do we need a graphics card and a CPU? So you said sometimes a graphics card. We always have a GPU in our computer, right? CPUs have a graphics processing unit built into the modern CPUs do, and it's also not uncommon for a motherboard to have kind of a backup system. If you've built a computer before, a lot of motherboards have built into it a VGA output port. Even newer ones have an HDMI or something, but they have onboard graphics support in the event you aren't going to provide a better one. Okay, so what's typically, if we're talking about GPUs, we're probably referencing the higher horsepower thingies. But at the end of the day, it's the computation thing that does a lot of the mathematical floating point math for making things show up on the screen. Why can't the CPU just do all that? Is the CPU capable of doing math?
Yeah, just has to do all the other stuff.
Oh, so the CPU's already busy. Right, modern day CPUs. What are some CPUs you've? Let me create another slide here. What are some CPUs you've heard of? Intel i7. So Intel Core i3, i5, i7.
Core Duo.
Core Duo. Intel Core Duo. That was kind of the generation before the I's. Okay. What came before the Core Duo? There's a Core Solo. Then you mentioned Pentiums. It was weird. What else? Celerons. Couple different bunch of generations of Celerons. So Celerons were kind of considered their budget pleaser chips. Pentiums were considered their more consumer level chips, and then you had the I think they kind of started mixing the names a little bit. Things got a little bit sketch, but all right. What about before the Pentiums? What do we have?
486.
Yeah, 486. We got even more interesting, right? We had the 486 DX2, 486 DX, 486 SX. So the SX was kind of like the Celeron. You know, that was the budget pleaser, but by budget pleaser, it meant $3,000 back then. So you had 486, 386, 286, X86, 8086, and all these had either an SX, DX, DX2 after them. Anybody know the difference between the SX and the DX? DX was the first processor to have an onboard math coprocessor. When you were just running an SX processor, you actually had to have a secondary chip on your on the machine to do math. Like doesn't that seem like something the processor should have in it? Math? And not the early ones. They did other stuff. Okay, so you had all these processors over the years. Which is the best? We didn't even talk about AMD processors in here, right? We have AMD. What's the current ones? They're Ryzen, Threadripper. I mean, they have cooler names, right? The Ryzen Threadrippers. Oh yeah, that just sounds good. AMD Athlons, AMD Opterons. Opteron was a cool name. Those were good ones.
FX series.
Yeah, those were back competition with the Pentiums. All right, so lots of different CPUs. What makes these guys different? Okay, what does that mean? So now we're back to the organization and architecture. What does architecture mean if we talk about these processors have different architectures? Well, what's inside of a processor? You ever looked at a processor? It's like this solid piece of silicon. I mean, think could just be made out of clay, right? It's just a solid thing, and on the bottom of it has a bunch of really fancy-looking little. The older ones had actual pins. The new ones have little magnet points, right? There's nothing in there except the expensive stuff you just spent a whole bunch of money on, right? So you mentioned logic gates. What are logic gates? Switches.
On and off.
Okay. Why do we need a whole bunch of those?
Because each one.
Okay, so this goes back to that whole CPUs are kind of a collection of magic tricks. They have this this instruction set associated with the CPU. So a whole bunch of magic tricks. We could tell the CPU to do this, then do that, then do this other thing. But inside the CPU, the way it represents those magic tricks is through physical things, right? Logic gates, wires, things like that are the, we almost can think about those, we can think about computer architecture like programming done with wires. Wires and logic gate things, which we'll talk about, and OR gates and XOR gates and NAND gates, NOR gates, and all sorts of fancy blah, blah, blah stuff. But at the end of the day, it's a computer program, usually something that solves a fairly small problem with a whole bunch of metal stuff, wires that are all soldered together. You know, when you do the prototype, now we have printed boards, so we're just printing metal. We'll talk more about that in a little bit too. But you know, ultimately, when you feed inputs in, so if you have a function in a real programming language that takes in 2 inputs, you know, 2 integers, let's say, and then it does something logically based on those 2 inputs, you get an output, perhaps. Well, with an implementation on a motherboard or on a processor with one of these magic tricks, you might have 2 inputs that come into it. Those are going to come in terms of electrical signals. Maybe one's on, one's off. Maybe they're both on. And that's going to go through some stuff and ultimately spit out either an on or an off. Rinse, lather, repeat a zillion times. Okay, and that's what these CPUs do. It's a whole bunch of little tiny programs created in hardware. Why would we want to create programs in hardware rather than software? Faster. Okay, they're faster. But what's the problem? So we prefer to do it in hardware because it's going to give us more performance. But what's the problem? Well, yeah, it is specific, but that's okay. You know, we look at all these processors here. We've kind of, you know, evolved this idea. If we go back to the early processors, you know, this is in the early days of computing. You know, somebody sat there and said, well, these are really let's just exaggerate it. Here's the 10 magic tricks that a CPU needs to be able to do to solve all problems. Well, then the next processor came out and says, well, here's the 14 that it really needs to do. We still need the old 10. Now we have 4 more that we need to do. Keep adding, and now we have hundreds of things each processor can. Actually, it's more than 1,000. Each processor can accomplish, and it's a superset of the previous architectures. Why does it have to be a superset of the previous architectures?
Backwards compatibility.
Backwards compatibility. But sometimes when you look at the, you get a new operating system or something like that, it says the minimum system requirements. You know, it'll say, Pentium, whatever, blah, blah, blah. So what it's really doing is it's saying we are using some stuff that was introduced in that architecture. So if you have an older architecture than that, our stuff won't work because we're going to be making magic trick calls to things you don't have. But usually, when you think about a Windows operating system when it comes out, for example, it runs on fairly old hardware, right? It doesn't require that you have last year's Intel Core i9 16-core processor in order to run the latest, greatest version of the Windows 10. Why not?
Apply to a bigger audience.
Well, why do I want to do that?
Make more money.
More money. Like, man, you got an old 8086 processor, it might work. It might work. I wonder what the minimum system requirements are for Windows 10. My guess is this is probably like a Core Duo or an early i3, maybe a first gen i3, something like that. But in any case, they're supersets, so you have backwards compatibility. But because they're only having to go back so far, at some point they could go back and change old things, right? They might go back and look at, the original Magic Trick 4. It's like, that guy either A, isn't necessary, or B, was wrong. That was an interesting thing. I think it was a Pentium 60 megahertz Pentium processor, one of the original Pentium processors that came out. And I said megahertz. This is before the gigahertz things. And I think that the architecture had a bug in it. I'm trying to remember what the instruction was, but this was a mass-produced chip inside of computers on people's desks that had a flaw, a logic flaw. That would be very difficult to fix, wouldn't it? Because now they got to send people new chips. Back then, it wasn't just a zero insertion force, drop chip in, lower bar, everybody's happy. Back then, it was, get the plier things out, pry chip off board without bending pins, put a next chip back on. It was kind of a disaster. So kind of an interesting thing. So you mentioned that we like doing things in hardware. So let me add a slide here. hardware versus software. So hardware, fast. What about software? What's the advantage of software?
Changeable.
Easy to change. What else can we say about hardware? Let's say we have the solution correct. Like, this is how it works. We don't need to change it. Would you always want to do it in hardware? What's the problem with hardware?
Single instance of it.
Okay.
It only exists one at a time.
Yeah, so maybe there's a production or a cost issue with it. Fine. Kind of fishing for our biggest problem with hardware. He mentioned something about a cooling unit earlier, or however you phrased it.
Physically takes up space.
It does physically take up space. What about heat? Is heat bad?
Potentially, yes.
Yeah. I mean, we're operating off a little bit different levels of heat. You know, a processor can run inside of a computer at a level of heat that would probably burn your finger without being damaged, but not much beyond that. So we need to control that heat. We need to dissipate it somehow, get it away from the processor. We do this with fans and copper tubes and all sorts of other things that, you know, heat sinks that disperse the heat away from the processor. What causes that heat?
Resistance.
So you mentioned we have all these little gates and stuff like that, transistors on these. A lot of times the complexity of a processor is measured in terms of the number of transistors on the processor. The more transistors we have, and the higher the clock speed of a processor. So that's something else to consider here. When we talk about CPUs, and we talk about clock speed. What are we talking about when we say clock speed on a CPU?
How many operations?
Okay. That's mostly accurate. So, you know, what are like an example of a clock speed in a processor today might be like 2.8 gigahertz, right? You might have a 2.8 gigahertz processor. Okay, so that's 2.8 times 1024 megahertz. Because you got 1024, blah, 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 blah. All right, so 2.8 gigahertz. If we think about that as number of instructions per second, this is probably 2.8 billion instructions per second. Now, having said that, is 2.8 gigahertz in one architecture equivalent to 2.8 gigahertz in another architecture?
No.
What would make it different?
How efficiently they're able to do each operation.
All right, so if we're trying to perform a solution, you know, like waving my hand, this is the solution we're doing, okay? And this is the human 1.0 architecture. so there was the elbow bend thing here, whatever. Okay, and now we're going to have I don't know, maybe it's a Mr. Gonzalez architecture. So he's less joints and things like that. Okay, so we have two separate architectures. Maybe the number of magic tricks it takes to do this in one architecture is more or less than it takes to do it in another architecture. So 2.8 gigahertz might not necessarily translate into pure performance difference. Make sense? Some problems are more easy to or can be represented in less instructions in certain architectures than other. And that's actually one of the big things with ARM, which we're going to talk about in here. All right, so clock speed is one way that we can compare two processors. So for instance, if we're looking at a processor with 2.8 gigahertz versus a processor with 1.0 gigahertz, there's not going to be very many examples where the 1.0 would actually outperform the 2.8 gigahertz processor unless it was operating in a much, much, much newer architecture that happened to have some magic tricks that are significantly evolved from the ones that were on the older architecture 2.8, and we happen to be using those exact instructions. Then maybe. then maybe it could be faster. But there's going to be a point of diminishing returns where if something has a clock speed that is substantially faster than another thing's clock speed, even if the architectures aren't, quite identical, it's probably going to outperform it in most tasks. And that's actually where things get a little interesting when a new processor comes out and you look at benchmarks. What are benchmarks? When Intel releases their new Core i9 processor, or there's a new graphics card that gets released, and they have all these benchmark numbers. What are those? What's the purpose of a benchmark?
Show how it performs.
Show how it performs. Okay, that's the goal of a benchmark, right? Show how something. Oh, we're talking about CPUs. Show how one CPU performs relative to another CPU. Okay. What is performance? What does it mean for a CPU to perform well versus another CPU to not perform so well?
Generally means it does things faster, one does better.
Okay. With an emphasis and a real kind of blurry thing going on with things. What do we mean by things? Typically, when Intel, for instance, and this is not just a demonizing Intel thing, this is when any company comes out with a new piece of equipment, they will release benchmarks that show it in its very best light. So they can say things like, oh, this processor is up to 60% faster than last year's model. Well, it's the same speed as last year's model in 98% of the instances, unless you do this one thing. We've added this one new magic trick that if you are doing this exact problem, is faster. So, is it worth getting that newest, latest, greatest processor? Maybe, if you're doing that kind of stuff. We see it even more in mobile devices. How many of you are iPhone users in here? Okay. How many of you are Android users? Pretty much 50-50. All right. How many of you have the most recent iPhone, either an iPhone 8 or the iPhone X? All right. So we had two people. Who has a Snapdragon 845 processor in there? Okay. So you have a Pixel 2?
Mm-hmm.
Okay, so you have Snapdragon 845. Is that 845?
I think so.
It might be the one right before that, but it doesn't matter. It's close enough. It's new enough. I think it's the one right before that. I don't remember which one it is, but it's fine. So her processor has an 8-core processor. It's an 8-core processor. Well, what does that mean? What about number of cores? What is a core as it relates to CPUs?
Physical instance of that architecture.
So we've already talked about these architectures. So we talked about a CPU that has this collection of magic tricks. So now they're saying, look, we're going to give you a single thing that you call a chip. You call this thing a CPU, but actually what's on this thing is 8 of those CPUs. She has 8 instances of that Snapdragon architecture, which is an ARM architecture. That's why we're using ARM in here. So we'll make some connections here eventually. But all right, now how many of you were newer iPhone people? We too. Okay, and so you guys have list last year's model. So you have the their latest, greatest. What is it? The A8, A9, A8 Bionic.
Yeah.
It's the A8 Bionic. Whatever. I think it is. I think it's the A8 Bionic. Chip. Do you have any cores your chip has?
6.
Yeah, 6 cores. 6 cores. Well, hers has 8 cores. Hers is better. 8's more than 6. What do you think? What do you think, iPhone people? Are your processors better than her processor? Oh, we should know. What does better mean? Depends what you're doing, right? Now, something they've done more recently, because we're going to spend quite a bit of time talking about mobile device type stuff too, but just to give you at the high level, you iPhone people, you have 6 cores, but only 2 of them are high-speed cores. You have 2 high-speed cores for gaming and stuff like that, for intensive things. And then you have 4 lightweight cores, doing simple tasks, stuff like that. Yeah.
It's the A11.
A11, so the next one will be A12.
Yes, it has an embedded M11 motion.
Yeah, that's been around for 3 or 4 years. All right, so you have 2 high-speed cores, so a higher clock speed version of the architecture, and then 4 lower speed cores, a lower clock speed version of the architecture in your inside your phone. Okay. Now, why did they put 4 lower speed ones in there? Heat. Those 2 higher speed ones, that's their trade-off. They said, look, sometimes you need performance, like when you're playing a game. So we're gonna deal with some heat then. But sometimes you're just checking your email. So rather than generate a bunch of heat just to check your email, we'll put that kind of stuff over on the low speed core, which can handle it just fine. Now, what you have over on the Snapdragon side, and they're starting to move away from this, is you have 8 equal speed cores. So more cores, but all of them would be what they consider high performance cores. Now, each of those individual Snapdragon cores are not as fast, generally speaking, as Apple's high-speed cores. Okay, I think the Snapdragon 845 actually has 4 and 4 high speed and 4 slightly lower speed, but it's less of a major difference. So they're moving in that direction. But in any case, you have more cores on one. You have almost as many cores, but less cores on another. So now we got to decide, when is more cores worth it? When does having 8 cores, when is 8 cores better than 6 cores?
You're doing 8 different tasks.
We're doing 8 different tasks, or how often are we actually doing 8 different tasks meaningfully? Typically, when we're on our computer, we might have some stuff running in the background, but maybe have 2 or 3 things we actually care about going on at once. But some tasks, you can divide the labor up. The example I historically will use, like if we're, when the fall, at the end of the fall, when the leaves start falling off the trees, and we have to rake up all the leaves on campus. If I can rake up leaves at a speed of 10, and we'll take 4 of you, and you could rake up leaves at a speed of 9, even though I can rake up leaves faster than any individual one of you, the 4 of you will be able to clear up campus more quickly, because that's a job where you can divide it up. You do this fourth, you do this fourth, you do this fourth, you do this fourth. Make sense? Okay, so some tasks you can divide up the work. More cores is then better for some of those things. All right. Now, generally speaking, in our computing today, we have, like I mentioned, 2, 3, 4 things that might be happening in the background that we care about. You're on your cell phone. You have some music playing in the background. Maybe you're browsing the web. You also want your email to be able to get, download new email messages. Maybe you also want Facebook notifications to be able to come in. So let's use that as 4. So you have 4 things that you want to be happening at the same time, right? So one thing you can do is you can have a single processor just switching between those things really, really, really quickly. And we'll talk about that in a lot more detail. But another thing is you can have individual processors, probably low-speed ones, working on those individual things, which aren't draining battery life drastically, but also have if you've had the operating system course, when you have to switch from one task to another, what's that called on the CPU? Context switching. And context switching is really, 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 really expensive. So the less you have to context switch, the better off you're going to be. So if we can have two physical low-powered processors working on two separate tasks rather than one, even the same power processor working on that task, but flip-flopping between, context switching between those two over and over and over again, you're going to get more performance out of your chip because it's going to spend more time working on the problem rather than context switching. Kind of make sense? So really, we're almost throwing darts. We're trying to decide how do people actually use their computers versus the number of cores we're going to give them versus the amount of heat that a processor is going to give off versus the clock. Well, not versus, but in terms of the clock speed we're going to run that at. Do we run all the cores at the same clock speed? Do we run some of them at a lower clock speed, some of them at a higher clock speed, and give certain tasks to each one? It's this giant question mark. We're just guessing. That's why they can say when each new processor comes out that it does a certain task better than it used to, because last year's idea was bad. It's like, we made a mistake. So I'm sure when the next, later on, in September, when Apple comes out with their next Bionic chip, their A12, I'm sure there'll be some speed boosts in it, and there'll be certain things that they'll say it's way faster at doing certain things. These will all be good stuff, but that doesn't necessarily mean that processor will perform faster for you. Depends on what you're using it for. Clock speed also isn't a great measurement. Would you all agree that our computers today are fast? Feels pretty fast, right? How many of you have built your own gaming machine, let's say, over the last 5 to 7 years? Like you've had multiple machines during that period of time where you've upgraded it, stuff like that. What's been your clock speed during that period of time?
I run like 3.2 gigahertz on 6 cores.
Okay, that's what you run today. What about 4 years ago?
Mine wasn't built then.
Okay. If you went back 4 years ago, you probably would not have found a significantly dissimilar clock speed. In fact, in many cases, you may have found a faster clock speed 4 or 5 years ago than you'd find today. Because as we've stuffed more and more stuff into the newer architecture, if we're going to run that at the same clock speed, what happens to the heat? Goes up, and heat's bad. So now all of a sudden, what are the cool kids doing with their gaming rigs? Liquid cooling, and I saw this video on YouTube where somebody took they did this open box setup for a thing, and then they just drop it into a bath of ether to keep it cool, which is an inert liquid, I guess. Yeah, I mean, we're doing all sorts of crazy things just to keep the cooling down. When I was in college a while ago, and I've told this story before in some of my other classes. You may have heard this before, but there was this guy who lived down the hall from me. This is back in the days of the Celeron, the old Celeron processors. This is during Pentium 2 days. So we had the Celeron chip, and one of the cool things about Celeron processors, the original ones, where you could just overclock the heck out of them, to the point of just not even being safe. And this is back, now they have motherboards that have overclocking stuff built into them where you can, this is back when you had to have jumpers. So if you had a 200 megahertz processor, you would probably run that at a 100 megahertz bus speed with a 2.0 clock multiplier, something like that. Well, this guy bumped all of his jumpers up. So he was running it at whatever the fastest bus speed was on his motherboard. Maybe it was 133 or 150 or something like that. And a clock multiplier of, he did a jumper skip. I think he was running at 18. So he was running this processor, I think it was designed to run at 300 megahertz, and he was running it at 2.2 gigahertz. And this is way before gigahertz was a thing. Yeah, you go to his room, he just had a fan pointed into his case. 3 or 4 in the morning one day, he goes banging on my door. I'm all the way at the other end of the hall. So I come out, and there are flames billowing out of his room. His entire room was on fire. And not just his whole room was on fire. everything in there. You couldn't go in there. So I had to have the fire department come in. I mean, his room was just charred. Everything was black. Yeah, so don't overclock too much.
Call the red door. You want to paint it black.
That was pretty funny. All right, so number of cores. More cores isn't necessarily better than less cores. In fact, for a long time, when multiple core CPUs were just starting to kind of become a thing, one of the things that was kind of a popular question for gamers was, do you get a single core processor that has a really high clock speed, or do you get a dual core processor with a lower clock speed? Because typically, the fewer cores you have, the higher the clock speed can get. Unless you have something that has, that wants you to have some crazy cooling system as a requirement for it, something like that. Okay, so we have all these things that are kind of at odds with each other. So when we talk about benchmarks, we're talking about the performance of, in our example here, one CPU versus another. But then we have to ask the question: what is performance? What makes one CPU better than another? And it comes down to, depends what we're doing, right? If we're playing a video game, we might care about certain aspects of a CPU. If we're doing video conversion, we might care about other aspects. Okay. As an example, let's say you're converting a long video. So something, I'm sure none of you have downloaded, a movie off the internet before, but let's say it comes in one format, you need to convert it to another format. There would be very, very, very few cases you would have to have a really slow clock speed, which I doubt something with this many cores would have that, where a 8-core processor would not perform better than a 4-core processor at converting that video. Because video conversion is something that can be divided up into pieces. So if you have 8 workers dividing that video up and converting that video at the same clock speed, you're going to do it close to 8 times faster. You still have some overhead for the operating system scheduling for those 8 cores, but it's going to be a lot faster. Even if you have 1 or 2 cores that individually are faster cores. Because converting video or doing video rendering, that kind of stuff, is a job that is greatly benefited by multiple cores. Whereas if you're doing one single task, kind of back to the whole idea of how many people does it take to change a light bulb? That kind of question. If I can change a light bulb at speed 10 and all the rest of you are on a really expensive processor and each one of you can change a light bulb at speed 9, and we're going to have a race who can change a light bulb the fastest, who wins? I do, because it's a one-person job, and I can change it at speed 10. Or even though all of you are waiting for extra work to do. Make sense? All right, so more cores doesn't necessarily mean better. Higher clock speed doesn't necessarily mean better. Better scores on a specific benchmark doesn't necessarily mean the processor will be better for you. There's a whole lot of stuff that are at odds for us when we're shopping for something or we're looking at upgrading our computer that are going to be hard for us to figure out. And this isn't just in CPUs, it goes across the board. You've probably had a class with me before where I've talked about your internet connection at home, right? Does everybody know what their internet connection speed is now? So I've berated you about it in the past. What makes an internet connection good? What makes an internet connection fast? Is a 1 gigabit connection better than a 400 megabit connection?
How consistent is it? How consistent is it?
They're both completely consistent. Same level of consistency.
Probably.
Probably. What if you're only checking your email?
Well, then you can check your email really quick.
Yeah, they're probably not any quicker because they both probably have the same latency.
But we wouldn't be able to tell the difference because it moves faster than
Oh, you'll definitely be able to tell the difference when you get your monthly bill.
I mean, in terms of speed when you check, because you normally know if the computer's faster.
Well, you're right. So getting a faster internet speed, more megabits, more gigabits, now they're selling gigabit internet, but whatever it is, if you currently have 100 megabits and you could upgrade to 400 megabits, you have to ask yourself, what am I using my internet connection for? If you're only checking email, or you're in an apartment by yourself and all you do is watch Netflix, Netflix is at most going to maybe use 60 megabits if you're doing 4K streaming or something like that. Doesn't make any sense to go up to 400 megabits, even though you might be tempted to. It's equivalent to you doing exactly what you do today, except you every month, on the first of the month, you walk out to the backyard and light 40 bucks on fire. Great YouTube video. This is the equivalent of upgrading your internet. So, what's better? What's faster? If you're a gamer, would you rather have a 100 megabit connection with a 9 millisecond ping or a 1 gigabit connection with a 50 millisecond ping? If you're a gamer, the ping is where it's at. So that's the amount of time it takes for you to communicate with the server. You're not using a whole lot of data to play your games, but you do rely on a really quick transition back and forth between the server you're connected to. So you'd rather have the slower max bandwidth, but the faster ping. That's better for you. Okay. If you're somebody who is addicted to downloading stuff off of BitTorrent, okay, and you'd like your machine running 24/7, and you're on, you're on 7 different VPNs, and it looks like you're coming from someplace in Turkey. That extra bandwidth is something you'd really like. You don't care about ping. Who cares if your torrent takes an extra, 19 milliseconds to start? Not going to notice that. But you're going to be pulling down a gigabit per second across all your torrents. Okay, so again, which is better? Depends on what you're using the connection for. Okay, computer hardware is the exact same thing. So it makes it very difficult for us, A, as consumers, and B, as technologists who are supposed to be experts on this, to give anybody a real clear idea on what they're looking for. When somebody comes up and asks you for many of us, we're the computer person and, to other people in our lives, right? My dad wants to buy a new computer. He calls me up and he says, this is what I want. First thing I'll ask is, what are you going to do with it? Should I go and get this $3,000 MacBook Pro, blah, blah, blah? It's like, no, why don't you get an iPad? Or why don't you get a $200 Chromebook, to do what he's going to do with it? It all depends on what you're going to be using the equipment for. It's not about the money. You can go spend the money on something else. You can get a 4K TV and the Chromebook, or you can just take a loan out for the MacBook Pro. you get the pick. All right. So one of the things that we're going to be grappling with over this semester is this idea of what speed means, what performance means. So we're going to care more about looking at two things in terms of how they're measured, in terms of determining whether one thing is better than another thing. Because better is all relative. Make some sense? Okay. Now, when we talked about some of this memory stuff up here, we talked about hard drives. This is slow memory. We talked about RAM, which is faster memory. Then we get to even faster memory. So a lot of times in our computers, we're talking about the faster something is, the more heat it typically gives off, the lower the capacity it typically has. These things are all at odds with each other. So when we think about our, like for instance, this laptop here, this we've heard of solid state drives, right? What's a solid state drive?
No moving parts.
Okay, so it's effectively what we've historically called our hard drive, but it's faster. It's not RAM fast, but it's faster than your mechanical hard drives, your HDD. So SSD is faster than HDD. Well, this laptop is a gaming laptop, so it has both in it. It has, I think it's either a 128 or a 256. I think it's a 128 gigabyte solid state drive where you keep your OS and maybe a couple of applications that you launch often. And then it has a terabyte hard drive, mechanical hard drive, where you put all your files, things that aren't getting loaded into memory every 5 seconds. Stuff that you're going to maybe is where you keep your images or your downloads, that kind of stuff. Okay, because these are things you're only going to use sometimes. So when you sometimes use it, then you're going to deal with that little bit extra time it's going to take for it to load from the slower hard drive, slower mechanical hard drive, through the bus up into the faster RAM. So your solid state drive can load stuff into RAM more quickly than your hard drive can, but they're both going to be slower than loading stuff from RAM to RAM. But if you're only going to launch an application once in every blue moon, are you willing to wait the extra half second to save some of that storage space in your solid state drive? Because generally speaking, you can go to Best Buy and get a 2 terabyte solid state or a 2 terabyte normal hard drive for $80. How much is the 2 terabyte solid state drive? More. Okay, it's more with a capital M, with several dollar signs at the end of it. Okay, and it's already come down in price. Okay, we're gonna talk about some of the pricing over the years as well. All right, so there's a lot of dynamics that goes into our hardware and stuff like that, and there's things that we need to understand as technologists, but there isn't a one size fits all type solution for some of these things. We have to ask ourselves, what are we using this for? I had a conversation with a guy after the opening ceremony the other day at the picnic dealie, and he is a embedded systems engineer. So he works on little tiny computers that are like embedded inside of air conditioners and stuff like that. And and from a general purpose computing perspective, we think about, oh, well, you mean if you're building a new computer and you have 16 gigs of RAM in there and you got an extra $50 to spend, just throw another 16 gigs in there, no problem. Okay, well, that's for a one-off machine that you're building. Just don't eat pizza a couple of times, something like that. Well, now you're talking about these embedded systems and how they're writing stuff in like C, and they need to get stuff as streamlined as possible. When we're writing software for general purpose computing, we typically don't care about how streamlined it is, right? It'll fit. We got a fast computer. We got 32 gigs of RAM. We got more hard drive space than I can pronounce. All this stuff. We don't care how big the code is. We don't care how big the compiled file is. It'll fit. Well, now he's in an industry where, the entire memory footprint on the embedded system they're working with might be 32 kilobits or 32 kilobytes. And if you can't get it to fit in 32 kilobytes, the next bump up the next part might be 128 kilobytes. Well, maybe the price difference between that and the 32 and the 128 is 30 cents. Does that seem worth it? It depends how many you're making. 30 cents adds up pretty quick if you're making hundreds of thousands of these little boards. So he's operating in that world, this optimization world of getting something that is pushing that limit of what will fit on 32K and keeping it on 32K so that you don't increase the manufacturing cost up to the next chip. Even from a one-off perspective, you're like, look, it's 30 cents. Who cares? Well, they're making a lot of them. Somebody's paying that bill. Make sense? Okay, so those are like the extremes, and they're things that all of us in this room can consider. Because when you're doing your programming homework, we don't think about that. Like, well, just comment out these 700 lines. It's fine. I might need them later. Okay? We don't care. That won't actually make it into the compiled code, but you kind of get the point I'm making. Okay, so types of CPUs, computer parts, motherboard we'll come back to, clock speed, important, but not necessarily the end all. Benchmarks, can't trust them. Number of cores, it depends. Hardware versus software. Okay, so hardware we consider to be relatively fast, but inflexible. Software we consider to be relatively slow, but flexible. Go in, change a couple lines of code, recompile, back to the office. Now, is there a hybrid? Because when we think about our computers, we want as much stuff to be fast as possible, right? That's a priority for us. We want stuff to be fast. What about flexible? How many go back to your 150 days? How many computer programs have bugs? Oh. What does Dr. Locklear say? 99.99, whatever. Most will have some bug in it somewhere, whether it's founded or not. It doesn't matter how hard we try, how much testing we do. It's going to be hard for us to check and solve every single bug. Okay, so now you have your piece of hardware out there in the wild, running on 1 million computers. And now you have a million different people using your stuff. Is there a higher chance that you're going to find one of those bugs than there was when you had 7 people testing it in the office? Yeah, a little bit. Okay, so now you got these 1 million people using it, and all of a sudden there's a bad bug. Do they send technicians out to those 1 million people's houses with soldering irons? Fix the stuff up? Well, that's how it would have worked a long time ago. Bring the chip back in, have them swap it out. What do we do now?
Release the patch.
Okay, how does the patch work though? If we want stuff to be fast and it's hardware, let's think about, go ahead. Firmware. Firmware, ever heard of firmware before? Okay, it's not completely hard. Firm. It's hardware and software glued together. All right, so you have certain parts of it that one of the things that your book will talk about, I'll flip to that screen here in a few minutes, but what time are we out? 25? 25, okay, I got some time. So one of the things, and sometimes you'll have to scream at me because I don't pay attention to the clock. But some of you know that already. So one of the things the book talks about is making the common case fast. There are certainly aspects of a lot of these problems. The thing that comes to mind is like our Wi-Fi routers in our house. You go out and get a new Wi-Fi router. There are aspects of that have been solved over and over and over and over again, where there are components of a Wi-Fi router that we could say likely does not have a bug. Right? Fair enough. Might be simple, fairly simple components. Those are the parts that get made pure hardware. But now you have a software system that sits on top of that talks directly to the hardware. So we can say that's pretty quick, because it's not relying on an operating system. So you're not passing the buck 4 or 5 times before something occurs. So we're going to say we're going to put some software on top of that hardware because this is this new stuff. Maybe you have the newest, latest, greatest Linksys router that just came out, and it's capable of the 802.11 triple Z or whatever the latest protocol is, and it just came out next week. So if this thing has not been tested in the wild, they don't even know when there's even going to be devices capable of connecting to it. That stuff you probably want to do in software. Yeah, you can test it internally. You're using, beta test parts that Qualcomm sent you that are technically compatible with that. But you haven't tested it on laptops that are actually shipping that have that compatibility chip in it and stuff like that. That needs to be in software so that they can, when stuff starts breaking, they can say, oh, here's the break, release the patch, and what do? You flash the firmware. Make sense? So firmware sits on very fast memory. So it sits on non-volatile, expensive memory. Is what it sits on. So typically firmware is very small. The actual capacity of it's very small. But it gives us that, so I'll just throw that as a buzzword in here. Firmware, best of both worlds. So now we can make a decision on what part can we trust and what parts do we want to give ourselves some flexibility for in the future. And now we've kind of decided on a balance between performance and flexibility. You will have better performance if it was all hardware. You might also have a bigger repair bill if you got to send a whole bunch of people out there to fix stuff. Now, the good news for us, though, and kind of something that makes this an easier decision for a lot of companies now, we mentioned it earlier in class, is computers are really, really, really fast. back in the 90s and 80s, computers were fast compared to humans, but not like they are today. You could tell the difference between, a 386 and a 486 computer. If you're checking your email on, I like to do it with Mac people. So if you have a Mac, anybody in here have a MacBook Air? Okay, so the super light, most underpowered MacBook you can get, right? But super portable. In fact, probably the machine that I've ever owned that I like the best was my 11.6-inch MacBook Air. Man, I have large pants, so that thing almost fit in my pocket. Close. That was a cool machine. Any of you have that machine? 11.6-inch?
Is that the 2015 one?
Yeah, it might have been.
Yeah.
But it's a super small one.
Yeah.
Because they had that, and then they have a 13-inch. 13-inch didn't make sense to me, because Apple laptops are already pretty portable. But the 11.6, that thing was small. So we're going to call that extremely underpowered for good reason, right? They had to make all that stuff fit in there. Okay. Now we're going to compare that to back in the same time period, the latest, greatest Mac Pro, not the MacBook Pro, the Mac Pro, with 8 processors in it, each with 4 cores. Okay. So now a lot of horsepower, right? A lot more money, a lot more computing power. Now we're going to have you check email with both of those. You're going to be able to tell the difference? I'll tell you what, I had both of those machines. Most of the time, I felt like the MacBook Air was faster. Seemed to be clickier, less stuff going on. I don't know. But you get my point? It really depends on how you're going to use that machine. So, it's very difficult for us to compare these things directly. Now, just to give you a little foreshadowing on what's coming next. If you go ahead and get the book, you might want to start reading through stuff. I won't give you a reading assignment yet, but over the next couple of classes, we're going to be talking about this section 1.2. So like 8 great ideas of computer architecture, this idea of Moore's law, how stuff keeps doubling in speed, although that's becoming less and less true today. We're going to talk about what's happening today. Abstraction stuff. Here's the common case fast thing I mentioned. Parallel processing, multiple cores, that kind of stuff. Pipelining, how do we set things up to be more fault tolerant, but also quicker and do partial pieces of a problem. Performance versus prediction. Can we guess at what the fast case might be and make that part really, really fast so that your solution is fast most of the time? Or some of the time, or none of the time? Things like that. The hierarchy of memories, closer you get to the CPU, the faster it gets. Okay, you kind of see these themes. All right, so questions, comments, concerns, bribes. So go ahead and make sure you get the book as soon as possible. Go ahead and do your Bible homework so you're good to go. And make sure you put a reminder in your phone for every Sunday, 5 p.m. or something. If you haven't done it, remind you to go and do it. And I'll see everybody on Thursday.